PPT. Yes, you can go ahead.
Okay, so thank you. So thank you participants for your patience waiting. So there was some technical glitch. So I think for the past 2 days we have been listening about the types of machine learning algorithms, supervised, unsupervised, and different types of algorithms. So today we'll be seeing other types of machine learning techniques, which is known as reinforcement learning. So I'll try to elaborate the topic, and I'll try to start from the basics of how the reinforcement learning has happened and what are the basic things there. And from that, we'll be continuing the coding part. I'll be trying to show you some example of a maze where the reinforcement learning is applied and how that algorithm is treated. Right? So here we'll be going through some of the basic things. So reinforcement learning is a type of technique where you'll be having, it is different from the supervised or unsupervised learning. So supervised learning will be having, for each of the input, you'll be having the output, so which is known as a labeled data. And depending on those training data, you'll be getting, you'll be training the data sets, and you'll be testing on some other things, and you'll be knowing about the performance issues, and you'll be testing on a separate data set. Right? So that you call it as a supervised learning. When we take unsupervised learning, we will not be having a labeled data. It is mainly related to unlabeled data. And some of the examples are like clustering algorithms. We have K-means clustering, hierarchical clustering, DV-scan clustering, like that. So this reinforcement learning, here what happens is you have something known as an intelligible, so intelligent programmable computers, right? So intelligent programmed computer is known as an agent, right? So that agent, it can be a robot or something else, or a human where a chip has been pursued. So here what you can do is you'll be making the agent to learn about the environment. So environment is nothing but the surroundings which are surrounded by the particular agent. So you'll make the agent acquainted with the environment, and depending on some of the actions which are performed by the agent, you'll be moving to some other different state. So right now you'll be in a particular state. From that particular state, it will be moving to another state. Right? So based on the actions performed, it will be going to a new state, and this process will be repeated until you'll be achieving the target place. Right? So the training is performed depending on something known as a feedback mechanism. Right? So if it is going for a correct point or correct type of thing, then you are getting a rewards. You are getting something known as rewards. So your rewards will be plus. If it is going, then if it is going in a wrong direction, your rewards will be minus. So there will be a plus point for a positive action and negative point for a negative action. Right? So here we have something known as so 1 second. Yeah. So now this is the agenda of this particular session, where we will be dealing with the introduction of the reinforcement learning and different terms which are used in the reinforcement learning, followed by the Bellman equation, so which is the basis for all the reinforcement learning algorithms. And next we'll be seeing the types of reinforcement learning, which are the types of reinforcement learning that are being employed. And you'll be dealing with the Markov decision process, which is the basis for all the modern reinforcement learning algorithms, and we'll be actually seeing the reinforcement learning examples and some of the applications, right? So this is the current
Unmute చేయటం. Unmute చేసినా? ఇప్పుడు
So the reinforcement learning is basically a feedback-based mechanism where the agent learns to behave in an environment by performing the actions. Right? So depending on the actions performed, we'll be calculating the rewards, and you'll be having a positive reward or negative reward. Right? So some of the basic examples of reinforcement learning is the maze environment, tic-tac-toe environment, chess, or some other gaming mechanism. When you take the complex examples, if you have a self-driving car, the autonomous cars, which are being developed now, so they are basically without a driver, right? So such complex examples can also be found in reinforcement learning. So when you see way back in 1990s only, there was a IBM Deep Blue chess machine algorithm which has competed with the then chess master Kasparov, and he has been defeated, right? So starting from that inception, there are many algorithms which have been developed. So ultimately, again, the person has defeated the computer. So there are many practical examples which are happening around, but to deal with our environment or to understand the reinforcement learning, we'll be dealing with an example of a maze environment. Right? So here we'll be understanding first the basic topics which are related to the reinforcement learning. So first we have something known as agent. So agent is nothing but which is acting upon the environment and who will be doing the actions, right? So next, environment is nothing but if a situation is surrounded in or an agent is present in a particular environment, we call that as environment, and it is appended with the E. So if you take some complex environment like a driving a car or something, or if you take some games, that will be the environment. And actions are the movement taken by the agent in that particular environment. So now you have a state. So state is nothing but if you are taking a maze kind of thing, if you are moving from one block to another block, that is known as a state. Right? So next you have a reward. So reward is nothing but if your feedback is something like a positive thing, then you will get a reward of +1, or you can do, take some rewards which you can define on yourself, and you can see that the agent get the maximum rewards while reaching the destination. And you have the last thing, which is a policy. So policy is where in a particular state, which action has to be performed. That is determined by the policy. Right? So policy is a strategy which can be applied by the agent so that he will move from the current state to the next state, or it determines the action which has to be performed by the agent. So now if you take a typical maze example, this is a simple maze example where we are having 12 different blocks. So now if the agent is trying to go from S9, this is the S4. So where you are having the diamond here. So if you take something like a robo. So if he is trying, so that he has to go here and pick up the reward. And when if there is a fire kind of something like that in this block, then he will get a reward of -1. So if he is going to a correct block, he will get the reward of +1. Right? So this is a simple example of a reinforcement learning where this robot has to understand this maze problem and he has to get this data. Right? So before going to the actual advanced reinforcement algorithm, we'll see the basic thing which has been followed where. Right? So the simplest technique which can be followed is you can start from S9. You can train the robot so that you can start from S9. And whenever he is making a movement, so if he wants to go to S5, he will place a 1 here so that he will say that the machine will say that I have visited this block. Next, it will go to S5. Similarly, it will go to S1. Right? Similarly, it will go to S2, S3, and so on. So if it is going and bumping here, so A6 is considered something like a wall here. So if it is bumping around and if it is not able to go here, then it will come back and it will see where it has to go, in which block there is no one has been placed, and it will go. Right? So this is a simple maze environment example. So here it is a basic kind of programming, but what here the main disadvantage here is if he is in a situation where it is a point of intersection and you have to move either to this point or this point, that is one step at a time, right? So if you are moving here or here, both sides it is placed as 1. So what the basic programming does is if it is not placed as a 1, it will be going there. It will place 1 and it will be moving to the next step. So now it is in a situation where both of the blocks are placed as 1. Right? So now there comes a problem. So where it has to go. So if it is going here, it moves in a wrong direction and it goes to a longer direction where it might lead to either diamond only, but it might take a long path. Right? So our main intention is to get it in a smaller path as well as to achieve the reward. Right? So by studying such kind of strategies, so Bellman, he has proposed an equation in way back in 1950s. He has proposed an equation which is known as the Bellman equation. So it is the basis for all the reinforcement learning algorithms. So this is the basic kind of technique which is applicable for all the reinforcement algorithms. So here what it does is, so this is the Bellman equation where you'll be calculating the value of a particular point or in a particular block, and here you'll be taking the max of reward at a particular state by performing an action. So what are the different actions you can perform in a maze is you can go either right, left, top or down, right? So depending on the action performed from a particular state, you'll be getting the reward. So if any reward you are getting, you'll place that value here. If no reward is there, you'll make it as 0, right? So there is a factor which is known as a discount factor, right, or gamma factor. So I will show you why you need this gamma factor later on. And V of S dash is the value at the previous state. So remember this one, it is the value at the previous state. So this was the basis for the reinforcement learning. Right? So now value calculated at a particular point is mainly dependent on reward at a particular state by performing that action and a value previously. So now if you train this particular maze which we have seen, the maze problem which we have seen, so we are getting the reward at S4. So it does not have any previous state. So there won't be any previous state for the robot. So what it can do is the machine, it can allocate the value of the previous state as 0. And what will be the reward from by going from S3? From S3, if you move to the right side, that machine will be getting a reward of +1. I told you if you are going to S4, it will be getting a reward of +1. Right? So that he has applied it in the equation. So max of R of S of A plus. So here you won't be taking any max values because there is no different movement. you are taking one step at a time here. If you are taking some complex problems, you'll be taking max of all these things. But here what it does do is, here if you are taking from S4, now you are considering the first block, S3, right? So from S3, if you are calculating the value at S3 here, so what will be the value of S3? Value of S3 equal to max of R of S3 is nothing but S3 comma A. So now if you are moving to the right side, any action is performing, and if it is getting the reward, so reward obtained will be +1. So R of S comma A will be 1. Right? So now V of S dash. So what is the value at the previous state? There won't be any previous state because S3 is the starting now which you are taking. Right? So again you are getting the reward here. So V of S dash, that is the V of S4 will be 0. So for V of S3, you will be taking only the reward which is obtained. So that will be max of 1. So you will be getting the value as 1 here for S3. Now if you go to the second block, right? So now if you go to the second block, here also you can apply the same principle here. Max of R of SA plus gamma into V of S dash. So here the previous state value for S2, that is nothing but from S3 it is coming to S2. Now you are training that it is coming from the target to the previous blocks. So now S3 value you are getting it as 1 here. That is the previous state for S2 because you are training in a reverse direction. Right? So from S3 you are going to S2. So previous block value is 1. But when you are going to S2 to the next state, you are not getting any reward here. The reward is placed only in S4. Right? So reward of the current state will be 0 only, while the previous state value will get it as 1. So reward of S comma A will be 0 because you won't be achieving any reward if you go here. And the previous state value, that is from S3 you are training to S2, coming to S2. So V of S3 value will be 1. So if you are applying this equation, max of R of SA plus gamma. So now gamma is 0.9, the discount factor. So 0.9 into 1. So you'll be getting V of S2 value as 0.9. Right? So now rewards of all the other blocks will already be 0 only because only for S3 will be getting the reward. Because if you are going from S3 to S4, then only will be getting the reward. Right? So all the remaining blocks will be having the reward of 0 only. While the previous state value will be dependent on your value which you are calculating here. Right? So the value will be 1 here. Next it will be 0.9. Similarly, if you apply the equation for the next one, here it will be changing to 0.81 because reward is automatically 0 only, but 0.9 into previous value again you have 0.9. Right? So 0.9 to 0.9 will become 0.81. Like that, the values of the full maze will be calculated. Okay? So you'll be calculating the values for the full blocks in the particular maze. So when you see the values which are obtained from the Bellman equation starting from the target value, these values will be entered. So V equal to 1, 0.9, 0.81, 7, 6. So now if it is in a situation where we have seen the disadvantage of the previous one where it has 1, 1. Now if it is the computer, if it is in a situation, the machine, it is in a situation of S1 state, now it can move to S2 only because it is increasing the value. Right? So the path will be taken in such a way that the value will be increased until it reaches the final state. Now, if the Bellman equation is applied like here, so now if it is starting from S9, the initial state, now what it can do, it can go to a state where it is maximizing the values. So from 0.66, it will go to 0.7, from 73, 81, 0.91, and at last it will be achieving the reward. Right? So now if it is in a situation at a point of intersection also, it can understand to which state it has to move. Like it can go down or it can go left, something else. Right? So in this situation, it will be going to S2 only because it will be trying to increase the value. That is the reward value. Okay? So this is the basic for all the reinforcement learning algorithms and the Bellman equation. So if you are calculating the values of all the mazes, so all the blocks in the maze, you'll be getting this kind of situation. So now if an agent, if he is trying to go from S11 and he is trying to reach S4, so it will start from 0.81 block value. And now if it has 4 options, left, right, top and bottom, right? So now if it is going to the left, it is decreasing, right, it is decreasing. So it will go to the upper value. So it is 0.9. Now from there it will go to 1 again. Right, so from there it will move to the right side where you will getting the reward. So left side automatically lesser value you will be getting the reward. Right, so such problems are clarified by the Bellman's equation. So this is the basic thing for all the Bellman for all the reinforcement learning algorithms. Right, so dependent on these, we have different types of reinforcement learning algorithms. That is, we have positive reinforcement and negative reinforcement. So positive reinforcement is where we'll be increasing the reward value of +1 or -1, and we'll be trying to maximize the reward. So such a maze kind of problem, we can take it as positive reinforcement. So negative reinforcement is a process where an undesirable stimulus is removed to increase the behavior. So here also the behavior of the agent is increased, but here we'll be removing that undesirable stimulus. So what does this mean is, if you are taking the example of a car in which where you are putting a seat belt, now what happens until you put a seat belt in new cars, there will be a beeping sound. So that undesirable stimulus is removed whenever you are doing a positive behavior, that is, you are keeping a seat belt. Right? So such kind of things you call it as a negative reinforcement. So there should be not like a full positive or full negative, it should be balanced. Okay? So as I told you, Bellman equation will be taking the values dependent on the previous state. But reinforcement algorithms, if you see, all the algorithms, they are mainly based on calculating or going to the next state only. So if you are taking the maze example, the machine will be trying to go to the next step. Or if you are driving a car or something like another games or chess games, so the next step has to be determined. So the previous states, they need not to be remembered. So for such kind of things, what they have done is all the reinforcement learning algorithms, they are trying to generalize it. So when they try to generalize it, they have come to a conclusion that all the reinforcement learning algorithms can be formulated as a process of Markov decision process. So there is a process known as Markov decision process. So all these algorithm or whatever you are seeing reinforcement techniques, all these can be taken and formulated as a Markov decision process. So this Markov decision process, what does it say? State is an agent constantly interacts with the environment and performs action. Right, so that is what is the reinforcement learning algorithm. And in each action, the environment responds and generates a new state. So an action is performed in the environment, and it will be generating a new state and a new reward. So this entire Markov decision process, it can be termed as in this way. So you have a finite number of steps and finite number of actions. So to go from a state to a particular state, you can apply these actions and you can transmit to a particular state. And RA is the reward which is obtained, and PA is the probability of choosing an action for a particular state. So when they formulated everything as a Markov decision process, this Markov decision process is mainly dependent on the Markov property, which states that this is the definition. So if you see, the main thing here is when an agent is present in a current state, say S1, if it is performing an action, it will move to the next state, S2. So now the current state depends on future action. So the current state and future action are only considered. So it is not considering the past actions or past rewards. So whatever is the current state and whatever is the action that is taking to the future state, those only should have to be considered. So you should not be considering the past actions or the past state. So that is what is specified in the Markov property. And from this property only, all the modern reinforcement learning algorithms have been developed. And while designing these algorithms, right? And when designing these algorithms, whatever equation we have seen, Bellman equation, that will be considered the basis for calculating the values in all the algorithms. So most of the algorithms will follow Bellman equation only and Markov property. So the Bellman equation, where you are taking the previous value of the state, now it will be changed, and you will be having just the current state, and you will be considering only the future action and the states. So it is not dependent on the past states or past rewards. Right? So based on this Markov property and Markov decision process, there are mainly three kinds of reinforcement. There are advanced also. Some of the basic reinforcement learning algorithms are Q learning, state action, reward state action, that is known as SARSA, and deep Q neural network. Right? So first we will go through Q learning. So this is an example. So like a maze example, we are taking a simple example to understand. So this is kind of rooms. So where it is numbered from 0 to 5. So there are total 6 rooms. Now if an agent wants to move from the starting room, that is 2, and if he has go to the finishing state, that is outside of this building. Right? So 5 is considered as some outside room or some outside state. So now if he wants to go from this state 2 to state 5. Right? So now what does Q learning do is, so you can graphically represent the states where you are taking the initial state as 2 and the different states from 2 to the goal state, which is 5. So here 2 is the starting state and 5 is the finishing state. Right? So from 2, what are the possible actions you can go to reach 5? So those are all depicted by this graph. Right? So from 2 to 3, 2 you can go to 3, 3 to 1, and 1 to 5. And directly from 1 you can go to 5, and directly from 4 you can go to 5. So here if you see from 1 there is an opening which you can directly go to 5. And from 4 you can directly come out. This is all entire 5. Right? So such kind of things. So from 1 to 5 you are going. So ultimately, if you are achieving the goal state, you are specifying the reward. So here reward has been specified as 100. So now if you are reaching the goal state, that means that you have achieved 100. That is how it has been established. So from 1 it has been going to 5. From if it is in the goal state also, we are going again to 5. So here 100 points have been specified. Sorry, hello. So here, maximum viewers are specified as 100 and minimum as 0. So when you are going from one state to another state, if there is any direction, so there is no direction where you are going from one state to another state, then it is specified. So that is initialized in this reward. So we have two matrices, one is Q and one is R. So R specifies the reward matrix. Q is the states from one state to another state which you are going. Right? So R is the reward matrix. So if you are going from one state to another state, if there is some direction to the another state, it will be specified as 0. Only if you are going to the final state, reward will be okay. So when you are going from one state to another state, so if you have any direction only, then it will be specified as 0. Otherwise, if there is no such kind of thing, it will be specified as minus. If you are going to the final state, it will be taken as 0. That is the reward matrix, right? So now what does Q-learning algorithm do? It will set the gamma parameter, which is a discount parameter, which we have seen, and it will initialize the reward matrix. So reward matrix has been initialized to the rewards, which we have seen earlier. And the Q matrix will be taken as all zeros in the initial state. Now, from that particular state, it has to go to another state, right? So from different possible actions, it will be selecting the current state, and from that particular state, it will be choosing a random next state, right? So, and it will be employing this equation. So this equation is Q of state comma action equal to reward of state comma action plus gamma into max of Q of next state comma all actions. So depending on these values, whichever is more, it will be going to the next step. Right? So whenever you observe this equation, you have something known as Bellman equation, which we have seen. That equation is modified, but here instead of going to the previous state, here is taking the values of Q for all the next states and all the actions have been considered here. Right? So for this particular problem, how the Q-learning algorithm works, we will see. So here we are taking Q of state comma action, that is 1 comma. Right? So action is nothing but one of the possible column values. Right? So from Q of state comma action, that is from 1, if you are applying 5, right? The action 5. So now what it goes to the next state, which is 5 only. Right? It will be going to the next state 5. But here you have to calculate the maximum values of the next state. So from 5, where you can go. So from 5, if you see here, so if you can see the reward matrix, which has been shown previously. So from 5, you can go to either 1 because we are having 0 here, or 4 or 5. That is a self loop. So if there is no direction or no path, it will be shown as minus. So from 5, there is a possibility of going to 1 or 4 or 5. So you'll be employing that in this particular equation. So Q of 1 comma 5 equal to R of 1 comma 5. That is reward of 1 comma 5. So if you are going to the immediate 5, so if 5 is your goal state, so you'll be achieving the reward of 100. So here reward will be placed as 100 plus gamma is the discount factor 0.8. Here in this problem, you're taking as 0.8 into max of all the next state values. So from 5, where it can go to either 1, 4 or 5. Right? So from 5 can go to either 1, 4 or 5. So this is dependent on maximum of Q values. So remember there are two matrices R and Q. So Q is initially all zeros. So all these values are zeros only. So that is why we are taking 100 plus 0.8 into 0. That is 100. Right? So now we'll update the Q value of 1 comma 5 to 100. So previously all of them were 0. Depending on this equation, which we are putting in Q learning, which is the basis from your Bellman equation, you'll be changing the value from 0 to 100. So this process will be repeated randomly for all the steps, and Q matrix will be updated each and every time. Right? So from if you are taking one state, it will directly go to the 5, which is the goal state. So the reward will be automatically 100. And from 5, if you are taking the next state and all the actions. So from 5, it can go to 1, 4 or 5. Right? But these values you have to take it from the Q matrix only. So here in the Q matrix, all of them are 0. So 0.8 into 0 will be 100. So we will be updating the Q matrix as 100. So reward is taken from the reward matrix and Q values are updated. Right? So this is the equation on which you are updating the Q matrix. So from this equation, again, if you are if you are considering a random initial state again. So first step, we have considered 1 as the initial state. Now, if you are considering 3 as the initial state, from 3 you can go to either 1, 2, or 4. Right? So suppose say we are going to 1. So Q of 3 comma 1. Now it is updated. R of 3 comma 1. So reward is 0 because 1. If you are going to one state, only 5 steps you will get 100. So one step you will get 0. 0.8 into max of from 1. That is from next state where you are going from 1. Which are the possible states is 3 and 5. So how will you get the possible state? You should go through the reward matrix. The algorithm will go through the reward matrix and it will see it is going to either 3 or 5. So here we have updated the previous state 1 comma 5. If you take the Q matrix, that value has been updated to 100. Okay? So max of 80, max of 0 and 100 will get 100. So 100 into 0.8 is 80. So Q of 3 comma 1 values will be 80. Right? So now this training will be done for all the initial states, and it will be seen that it will converge to a particular value. So whenever the convergence is applicable, those values are stored into the agent's chip or brain. Right? So when you are taking this matrix and when all the training is performed, so you call them as different episodes. So when you reach a final state, it is known as one episode. So if you are taking random initial states and if you are going to the final state, you will get this final matrix. Now you have done for 1, 3. Now you can do for another states. So such actions are performed. And at last you will be getting the Q matrix in this. So when you are getting the Q matrix, again it will be normalized. So normalized nothing but the highest value it will be divided. So 500 by 500 into 100. So that will be 100. So maximum value will be taken as 100. So 400 is nothing but 400 by 500 into 100. That will be 80. So this will be normalized. So after rigorous training, it will be converged. So the maximum values will be obtained, and you'll be training that, and you'll be dividing by the highest value, and you'll be getting the Q values. Right? So these Q matrix will be fed into the agents algorithm. Right? So depending on the algorithms, it will be fed into the agent perspective. So now when you see here, all the Q values have been updated. So if you are taking initial value as 2, if you are moving to 3, so depending on the Q matrix only, 2 to 3, 64 value. Right? 3 to 1, 80 and 80. So such kind of all the paths are updated with the Q values. So now what does your agent do? Now it has to move from agent from room 2 to goal state 5. Okay. So what does it do? It will consider this state and it will go to a higher value. So 51, 64. So here it will go to a 64 value. From 3 it has 2 options again, 4 and 1. Now it can go to a higher value, 80. Okay. So from 1 again it will go here and it will reach the goal state. So now you are seeing that at each step you are going to the higher value and you will reach the final state. Right? So on the basis of your Bellman equation only, this Q learning algorithm has been developed, and you have basically two matrices, Q matrix and R matrix. And depending on the Bellman equation, it has been changed to consider the future states instead of the previous states. And you'll be going through the matrix and you'll be updating the Q values. So at last, you'll be trying to maximize. So you'll be taking the edge, which is having the highest value, and you'll be reaching the goal state. Right? So now if you want to maximize the total rewards, you can take another path. So depending on the algorithm, it can go. So the Q learning algorithm works in this. So this is the theoretical part of Q learning. So we'll try to see the coding part where we have taken this implementation. See here, sir. Are you able to see the coding window? Okay. Thank you. Right. So here we are taking a package and we are importing into our current IDE. And here we are taking the edges pointing from 0 to 10, 0 to 9. Oh, sorry, 0 to 10 only. So here, starting from the node 0, the agent has to reach the goal of 10. So your goal state is 10 and starting state is 0. And depending on these edges, a graph has been constructed. So this is the code for generating graph where you have for X package, and when you call a graph function, it will be generating graph, and you can add the edges. Spring layout is nothing but each of the nodes will be considered as objects attached to a spring, and the edge will be considered as a spring. Okay? So and the edges will be drawn like this. So if you are taking 0 to 10, so this will be the shape of the graph. So from 0, the agent has to go to 10. So that is our problem statement. And how will you achieve it using this Q-learning technique? Okay. So if you see, only when you are going from 9 to 10, you'll be getting the reward. That is from 9 to 10 only, you have a path to directly go to the goal state. So you are taking the reward as 100 here. We are mentioning it. Reward, that value can be specified by you in programming. So from 9 to 10, I am going here. So only the columns, the value at the intersection of 9 to 10 will be updated to 100. And you can have a self-loop. If it is a goal state only, it can be 100. And if you don't have a edge, so 0 to 6 you have a edge, so you'll be keeping it as 0. 0 to 1 you have edge, you have been keeping it as 0. But when you take 0 to 5, there is no direct edge here. So you'll be keeping it as -1. That you will be doing it in the next. Okay? So whatever you have seen in the Q learning in the theory, the same thing will be applied here. So initially there will be 11 rows and 11 columns matrix will be taken, and it will be initialized to 1. And when you multiply by -1, all of them will be initialized to -1. Right? So you have taken all the points, right? So you have taken previously all the points here, that is 0, 1, 1, 5, 5, 6, all these. So if that particular edge is existing, and if your goal, that is point of 1 is nothing but if the second value is 10, that is your goal is 10, then you make that point as 100. That is that particular edge as 100. So in that particular matrix, row 9, 10 will be placed as 100, because 9, 10 value if you take, 10 is the first value. So 9 is 0 and 10 is the first value in that particular edges. So since you are getting the goal as 10, that point will be placed as 100. So 9, 10 value will be placed as 100 in their matrix. Else all of them will be put as 0. But that point should be in the edges, which we have specified. Right? So that matrix we are taking like this. So whatever initialization we have done previously in the theoretical part, if there is an edge, we are putting it as 0. If there is no edge, it will be put as -1. And if we are reaching a final state, that is 9th row and 10th column, so you are specifying it as 100. That is 9, 10. Right? And goal is nothing but 10, 10, which is the self-loop, will also be placed as 100. That is the reward which we are taking. Right? So this is the initial matrix which we have taken, and we have named it as R in the theoretical part. Now we are naming it as M here. Right? So M is the reward matrix, and Q will be our matrix where we'll be updating the values. So Q is a matrix where we will be taking them and initializing all of them to 0 only. So all of the rows and columns will be initialized to 0. And we'll be taking a discount factor, which is 0.75. And here we have considered the initial state as 1. We can take any state and we can train it. Right? So available actions are nothing but from a particular state, what are the different available actions? So what are the available actions we have seen? Only if that particular row and column has a value of 0 or more, only those values have to be considered as a next available action. Otherwise, there will be -1. So there won't be any possibility. So that code is specified here. Right? So current state row is nothing but whatever initial state you have taken, that particular row will be taken, and in that particular row, whose values are greater than or equal to 0, only those will be taken. So who are having greater than or equal to 0 values, only those will be considered, and in that particular row, that column value will be considered as available actions. So for one, we might have different available actions. So you can go to 5 or 6, something like that, depending on the matrix. Right? So those available actions will be returned here. So it can be more than one. Right? So from those available actions, what we are doing is you are generating a sample next action. That is, from those available actions, you will be generating and you will be taking only one random action. That is given by this code here, np.random.charge. And comma 1 is nothing but among the values you give me only one value, which will be considering it as the next action. Right? So sample next action will be giving the next action which can be performed, and available action is nothing but what are the available states, Right? So for that, from that you will be updating your Q learning matrix. So you will be taking the matrix and you will be updating it. So how you are updating it? You are taking the Q values of next state, comma all the actions. Right? So here Q is nothing but M. So we are taking M of current state based action, that is reward, plus gamma into max value. So how you are getting the max value is you are considering the Q of all the actions and the maximum state. Right? So whatever the maximum values are there, that you are getting here, and only the action which has to be performed for the maximum value will be taken, and that is kept in max value. So that code is specified here. So here, if you take line by line here, you are taking the action, and whichever is having the maximum value in that particular code, that will be taken. So you have to take the maximum value in that particular code. Suppose if you are having the same maximum value for both of them, now what it is telling, you give me a random one and give me one value. So that will be considered as the maximum index. So maximum index is nothing but the position of that particular maximum state. Right? So depending on that, you will be getting the maximum value from the matrix. So now you are employing the equation which you have seen in theory, Q of current state comma action equal to reward of that state comma action plus gamma, that is discount factor, into max of all positive states comma value. That is nothing but here we are storing it in the max value. The same thing is applied here, and whenever you are getting the value as greater than 0, so I told you we'll be dividing it. So in the previous example, you have seen maximum value attained is 500. So you are dividing each value by 500 and multiplying by 100. So the same process is done here. Right? So that method is called and the same procedure is done. So this is the main calling of all the functions. So here available actions is called, where you will be getting all the possible available actions. And from that, a sample action is taken, and from that, the score is updated in the matrix, and you'll be updating the matrix by appending. Okay. So this will be done until you will reach a state of 10. So your final state is 10. So you'll be repeating this process until you reach the final value of 10. So here he is repeating the steps. So whatever steps we are taking, that is repeated, and most efficient path is obtained. That is the most obtained reward in this path. So your path will be 0, 1, 3, 9, 2. So if you take the initial graph here, so it will go from 0 to 1, 1 to 3, 3 to 9, and 9 to 10. So this is the most optimal path. So that has been generated. And the rewards also has been calculated depending on the number of iterations. So here he has taken 1000 iterations, so that it has been trained 1000 times, and he will be getting the most efficient. Right, so this is an example of Q learning and how it has been implemented. So the same example you can apply it for a real-time example, where in the zero node you can specify it as a detective. So what this detective is trying to find is the drug racketing areas wherever it is there. So what the detective assumes is those drug people who are selling the drugs, they might not be in areas where the police vigilance is more, and they might be nearer to the areas where the drug traces are more. That is something like while preparing those drugs, something has been left. So from there, it can reach the actual location fast, and it will be not closer to the police location. Right? So your nodes can be replaced with all these values, and the same procedure is applied. So here 0 to 10 have been again renamed, and middle states have been put like that only. And from 0, that is the detective, initially it goes to 1. From 1, how we can go to the actual rectification center. That is the current scenario. So using Q learning technique and using the same procedure which we have seen. So previously what we have done is we have taken the reward matrix. Here we have to train the agent with police environment as well as drug environment, that is drug traces environment. So wherever police is found, that will be increasing in the matrix, and drugs where it is found, that will be increasing. So that those values will be updated. Right? So depending on those values, the training will be performed and will be going to the script. So the same kind of procedure only will be renaming, and you can apply with the practical example. So here it has been trained with the police nodes as well as the drug traces. And you'll be going with the maximum values which are found, and the same Q learning technique will be applied, and the action will be chosen. Right? So this is an example of your Q learning technique. And when you go to the next type of algorithm, that is SARS algorithm, is original state, action, and reward, and a new state and action. So the main difference between Q learning and SARSA is maximum of all the next states will not be taken. It will be considering only one value instead of going through the maximum of all the values. Right? So for implementing this SARSA example, we have taken the frozen lake environment example, which is a part of GIM package. So GIM is used to simulate all the reinforcement learning algorithms. So here S can be taken as a starting state and G as a goal state. So this is a frozen lake where you have holes here where you can fall down, and how you can reach a goal state by going through the frozen state. Right? So that is the algorithm here, and so there is no time to go through the steps. So practical implementation like this. So where you can import the frozen lake environment. Here you have a GIM package, so where you can import that. And it has been trained for total 10,000 episodes. Episode is nothing but we are going to a goal state. That is considered as one episode. So it will be trained according to So observation space and environment space is nothing but we have seen all the values, right? F and S. Those will be in the numerical values. Those all will be placed here. So ENV is a environment variable where you can get all these values directly. Right? So instead of going to all the Q learning and going to the next thing, what it does is here you have a step method. That is, you can choose a random next step. So depending on that step, you'll be getting the next state reward. Done is nothing but if it has reached the final goal. So like this, you can update the Q value. You can update the Q value accordingly. So these are nothing but the steps. So the entire block which you have seen there is from starting from S to goal point, how it is moving up or down or left or right, and how it is reaching the goal. So we are taking 10,000 episodes, that is 10,000 times, but here the output is shown only for 5. So the different training techniques will be taken. It will be taking the random initial state starting from S. Next it will take from here. So like that it will be taking, and it will be updating the matrix. So depending on the updated matrix, it will be going to the rewards and it will be increasing. The whole thing is performed. So next you have something known as deep neural network. So this is where you already know that neural network, it will be doing the process itself. So you'll be getting the maximized Q values instead of going through step by step, initializing them and getting the max value in each row. This all will be taken care by the neural network itself. And the Q table will be updated. Okay? So you have to train the neural network, and whatever the optimal value is there, that is taken, and the testing is performed on the particular neural network. So the hidden layers and everything has to be trained. So this is the basic difference between your Q learning algorithm as well as deep Q learning techniques. Here the Q table is placed, and each time for performing an action, the value is updated and will be going to a new value, and will be taking a new value. In the deep Q learning, all this will be taken care by the neural network. You have to train them, and will be getting the maximum values. So these are the basic differences between your reinforcement learning and supervised learning. So reinforcement learning works by mainly interacting with the environment, and whereas supervised learning mainly works on the existing data set. So it will be working better where the environment is AI related. So here no label data set is present in reinforcement. So depending on the environment and whatever the actions it will be taking, it will be trained and it will be updated. Here a label data set will be present. So here no previous training will be provided. So the training can be provided only, but there won't be specific output for each of the inputs. So it will be trained automatically and testing can be performed. So these are the different applications where the applications of reinforcement learning. You can have it in robotics, which we have seen in their example, as well as chess and something. So game playing is where you can employ for chess or Pac-Man games or tic-tac-toe games, chess games, and finance sector is where you'll be automatically giving the values of the trades and the inputs, and it will automatically get trained to that particular environment, and it will be giving the final. So manufacture related is nothing but the autonomous cars which have been prepared, so which are in process and will be getting it soon. So these are some of the applications of RM. So these are the main things we have seen: the Q-learning algorithm, SATSA algorithm, and the basic deep Q-learning and the practical. So this is from our side. So
So participants, if you have any kind of the queries, you can post it in the chat. Thank you, Dr. Santosh, for giving the valuable information on the reinforcement learning. The next session will be handled by A. Vishnuvardhan Reddy, 2:30 p.m. So break for lunch and we shall resume at 2:30 p.m.